In the last section, we were talking about the need to be able to solve for a variable that's in the exponent. And so we realized we didn't have an operation that was going to get the variable out of the exponent. So that's why we needed to invent something. And so we just invented together logarithms. Do you know that? We just invented it. We invented it so that we could solve for a variable in the exponent. So the logarithm of x base b is written log base b of x equals y. And here the base has to be greater than 0 and the base cannot equal 1. So the definition of a logarithm is you have exponential form and you have the logarithmic form. So the logarithm essentially is equal to the exponent. You see, if you take a base and you take it to the power, I'm going to call it p for power, even though here it's x and y. So if you take the base to a power, you get a number, correct? Like, for example, if you take 2 to the third power, you get 8, okay? So the logarithm is the inverse of that. It gets that power out. The logarithm is equal to the power. So you have log base b of a number gives you the power. So for this example, if I was going to write this exponential expression, or exponential equation really is an equal sign, if I was going to write it in logarithmic form, I would say log base 2, because that was the base, right, of a number, and the number is 8, is equal to the power. And the power in this case is 3. So the logarithm asks the question, 2 to the what power gives me 8? And that answer is 3, right? So when you see this log base 2 of 8, you could start to fill in what you know. You know the base is 2. You know the answer is 8. And then you're looking for that exponent. So let's try a few here. The base is this little tiny number. We read this log base 3 of 9 is 2. Log base 3 of 9 is 2. Well, that means that 3 is the base is equal to 9. What was the exponent? 2. So you're just putting this using the definition of logarithms. We take it from logarithmic form to exponential form. Why is this exponential form? Is because you have a base to a power equals a number. Okay, now this one is in exponential form. It's saying 5 to the negative third power is 1/25. Does everybody agree with this statement? Does this statement make sense? So now let's try putting it in logarithmic form. We're going to say log base what? The base is 5. And the number is 1/125 is equal to the exponent that gave it that. The exponent is -3. Okay. Log base 10 of 10,000 equals 4. How would we write that in exponential form? The base is 10. The number you get is 10,000. What exponent did you need? 4. 10 to the 4th power is 10,000. Okay, let's put this one. This is already in exponential form. Does everybody agree that 15 to the 0 power is equal to 1? Okay, what would be the log form? Log of the base. What's the base? Log base 15 of what number? 1 equals 0. This says 15 to the 0 power is 1. Log base 1 is 0 means 15 to the what power equals 1. And there's your 0. Okay. The log asks or answers the question, what was the exponent? All right, here This is saying 3 to the what power equals 9? And so what would the power be? 2. So that means log base 3 of 9 is equal to 2. Okay? If we're going to write this in exponential form, I think it's really much easier to write it in exponential form. We're saying 3 to the what power, because that's what we're going to get, is the power, equals 1/9. Can anyone think about 3 to the what power gives us 1/9? -2. -2. Yes, -2 is our answer. 25 to the what power equals 5? 25 to the... What do you do to 25 to give you 5? The 1/2 power. Why do you say 1/2 power? It's the square root, right? The 1/2 power, x to the 1/2 power, is equal to the square root of x. You just remembered something all the way back from chapter 7. Woohoo! Rational exponents. If you can't remember rational exponents, you might revisit chapter 7. I can't remember which section it was. Okay, this says 2 to the what power equals 1/16. So that's what we're going to get is the power. Can anyone tell me? 2 to the what power gives you 1/16? See how I'm just writing it in exponential form to help give myself a clue. In order to get the reciprocal, I needed a what kind of exponent? Negative exponent. So I know the exponent has to be negative. -4, because 2 to the 4th power is 16. And so 2 to the -4th power is 1/16. Okay, from the last section, we graphed 2 to the x. So the y-intercept, does anybody remember what the y-intercept was? When x equals 0, what would y equal? 1. Good. What was the x-intercept of 2 to the x? Yeah, there was none. Was there any asymptotes? Y equals 0. What was the domain of this exponential function? Yes. And what was the range? Okay. Now I want to graph this. So here's my y-intercept. 2 to the 1st power. We can do our table if you want, x and y. 2 to the -2, -1, 0, 1, 2. 2 to the -2. Does anybody remember what that was? 1/4, 1/2, 1, 2, 4, right? 1, 2, 2, 4, 3, 8. Here's -1/2. We had really, really tiny, tiny, tiny numbers. That's what created our asymptote. Okay, so we have an exponential decay or growth. And why is it growth? Yeah, as x goes more positive, our numbers are growing larger and larger. So we have exponential growth. Okay? But because we just learned about the logarithm, we actually can find the inverse of this function. So if we have 2 to the x, let's remember how we find the inverse. What was our very first step in finding the inverse? And we will need the definition of logs. So to find the inverse, the very first step was replace the f of x with y. So y equals 2 to the x. Then what do? Yes, you swap the x and y. So now we have x equals 2 to the y. But hey, I want to solve for y. I want to get y by itself. So how would I get y out of the exponent? Well, I said if I have a base to a power equals a number, we could use the log. Log base 2 of x equals y. You see how I did that? Using the definition of logs? Now, what's the inverse? F inverse of x is equal to log base 2 of x. If we were to check it, and I will say that's where people lost some points, right, on the test, was forgetting to check it, and even though I made it a big deal, to check it, we would do the composition of functions. And what should happen is they should be inverses of each other. So if I plug this inverse into the original, I would get 2 to the log base 2 of x. Well, that should be x by definition, right? If I did it the other way, if I take the inverse of f of x and I plug in f of x here, I plug it in, right? I'm going to have log base 2 of 2 to the x. I think this one is a little bit more obvious, right? This is saying a base of 2, 2 to the what power gives me 2 to the x. You see, using the exponential notation, 2 to the what power gives me 2 to the x. What's the missing exponent? X, right? The only thing that would make this true is if I have x here. So what we've just shown is that log base 2 is the inverse of 2 to the x. What do you think the inverse of 3 to the x is? It's log base 3 of x, I should say. So this would be another example of inverses. Okay? Any questions on that? I realize